In computer science, parameterized complexity is a branch of computational complexity theory that focuses on classifying computational problems according to their inherent difficulty with respect to multiple parameters of the input. The complexity of a problem is then measured as a function in those parameters. This allows the classification of NP-hard problems on a finer scale than in the classical setting, where the complexity of a problem is only measured by the number of bits in the input. The first systematic work on parameterized complexity was done by Downey and Fellows, under the assumption that PNP. There exist many natural problems that require superpolynomial running time when complexity is measured in terms of the input size only, but that are computable in a time that is polynomial in the input size and exponential or worse in a parameter. Hence, if is fixed at a small value and the growth of the function over is relatively small, then such problems can still be considered tractable, despite their traditional classification as intractable. The existence of efficient, exact, and deterministic solving algorithms for NP-complete, or otherwise NP-hard, problems is considered unlikely. If input parameters are not fixed, all known solving algorithms for these problems require time that is exponential in the total size of the input. However, some problems can be solved by algorithms that are exponential only in the size of a fixed parameter while polynomial in the size of the input. Such an algorithm is called a fixed parameter tractable algorithm, because the problem can be solved efficiently for small values of the fixed parameter. Problems in which some parameter is fixed are called parameterized problems. A parameterized problem that allows for such an FPT algorithm is said to be a fixed parameter tractable problem and belongs to the class. And the early name of the theory of parameterized complexity was fixed parameter tractability. Many problems have the following form. Given an object and a non-negative integer, does have some property that depends on. For instance, for the vertex cover problem, the parameter can be the number of vertices in the cover. In many applications, for example when modeling error correction, one can assume the parameter to be small compared to the total input size. Then it is interesting to see whether we can find an algorithm which is exponential only in, and not in the input size. In this way, parameterized complexity can be seen as two-dimensional complexity theory. This concept is formalized as follows. A parameterized problem is a language where is a finite alphabet. The second component is called the parameter of the problem. A parameterized problem is fixed parameter tractable if the question can be decided in running time, whereas an arbitrary function depending only on the corresponding complexity class is called FPT. For example, there is an algorithm which solves the vertex cover problem in time, whereas the number of vertices and is the size of the vertex cover. This means that vertex cover is fixed parameter tractable with the size of the solution as the parameter. Complexity classes. FPT contains the fixed parameter tractable problems, which are those that can be solved in time for some computable function. Typically, this function is thought of as single exponential, such as, but the definition admits functions that grow even faster. This is essential for a large part of the early history of this class. The crucial part of the definition is to exclude functions of the form, such as the class FPL is the class of problems solvable in time for some computable function grower. FPL is thus a subclass of FPT. An example is the satisfiability problem, parameterized by the number of variables. A given formula of size with variables can be checked by brute force in time. A vertex cover of size in a graph of order can be found in time, so this problem is also in FPT. An example of a problem that is thought not to be in FPT is graph coloring parameterized by the number of colors. It is known that 3 coloring is NP-hard, and an algorithm for graph coloring in time for would run in polynomial time in the size of the input. Thus, if graph coloring parameterized by the number of colors were in FPT, then P equals NP. There are a number of alternative definitions of FPT. For example, the running time requirement can be replaced by. Also, a parameterized problem is in FPT if it has a so-called kernel. Kernelization is a pre-processing technique that reduces the original instance to its hard kernel, a possibly much smaller instance that is equivalent to the original instance but has a size that is bounded by a function in the parameter. FPT is closed under a parameterized reduction called FPT reduction, which simultaneously preserves the instance size and the parameter. Obviously, FPT contains all polynomial time computable problems. Moreover, it contains all optimization problems in NP that allow a fully polynomial time approximation scheme. W hierarchy. The W hierarchy is a collection of computational complexity classes. A parameterized problem is in the class Wi if every instance can be transformed to a combinatorial circuit that has width at most I, such that if and only if there is a satisfying assignment to the inputs which assigns 1 to at most k inputs. The height thereby is the largest number of logical units with unbounded fan-in on any path from an input to the output. The number of logical units with bounded fan-in on the paths must be limited by a constant that holds for all instances of the problem. Note that FPT equals W0 and Wj for all. The classes in the W hierarchy are also closed under FPT reduction. Many natural computational problems occupy the lower levels W1 and W2. W1 examples of W1 complete problems include deciding if a given graph contains a clique of size k, deciding if a given graph contains an independent set of size k, deciding if a given non-deterministic single-tape Turing machine accepts within k steps. W2 examples of W2 complete problems include deciding if a given graph contains a dominating set of size k, deciding if a given non-deterministic multi-tape Turing machine accepts within k steps. Wt can be defined using the family of weighted depth SAT problems. For is the class of parameterized problems that FPT reduced to this problem, and here, weighted depth SAT is the following problem. Input: a Boolean formula of depth at most and width at most, and a number. The depth is the maximal number of gates on any path from the root to a leaf, and the width is the maximal number of gates of fan-in at least 3 on any path from the root to a leaf. Question: does the formula have a satisfying assignment of Hamming weight at most? It can be shown that the problem weighted normalized SAT is complete for under FPT reductions. Here, weighted normalized SAT is the following problem. Input: a Boolean formula of depth at most with an AND gate on top, and a number. Question: does the formula have a satisfying assignment of Hamming weight at most? WP is the class of problems that can be decided by a non-deterministic polynomial time Turing machine that makes at most non-deterministic choices in the computation on Flum and Grower. It is known that FPT is contained in WP, and the inclusion is believed to be strict. However, resolving this issue would imply a solution to the P versus NP problem. Other connections to unparameterized computational complexity are that FPT equals WP if and only if circuit satisfiability can be decided in time, or if and only if there is a computable, non-decreasing, unbounded function f such that all languages recognized by a non-deterministic polynomial time Turing machine using flog n non-deterministic choices are in P. XP is the class of parameterized problems that can be solved in time for some computable function.